Welcome back to another exciting episode of Chemistry, the high school edition. Intermolecular forces are the forces between molecules. So think about this. Why does water become a gas at 100 Celsius and carbon dioxide become a gas at negative 78 Celsius? Carbon weighs more than carbon dioxide. Carbon dioxide weighs more than water, but water boils at such a higher temperature. So the answer to this is intermolecular forces. And intermolecular forces are expressions of the interactions of molecules based on their polarities, based on their masses, based on a lot of things like that. This is the same reason why a gecko can climb glass, is because it has very finely divided fibers on its paws, on its little toes, that allow it to have a lot of intermolecular force attractions with surfaces and climb up them. So, relative magnitudes of forces. The types of bonding forces vary in their strength as measured by the average bond energy. So the first one is not an intermolecular force. This is an intramolecular force. This is a force that's within a molecule, but it's more as to give us a reference. So a covalent bond has an energy of about 400 kilocalories per mole. Now, the first intermolecular force, the strongest intermolecular force, is hydrogen bonding, which is about 12 to 16 kilocalories per mole. You'll notice how much lower they are relative to a covalent bond. And this is important because it's much easier to separate things, intermolecular forces, than it is their intramolecular forces. You have to break apart molecules to break the covalent bonds, but hydrogen bonding can be broken by turning something into steam. Or into a gas. Dipole-dipole interactions a little bit lower, a little bit weaker. These are based on multiple polar molecules interacting with one another and being attracted to one another. The next is London forces, which is less than 1 kilocalorie per mole. London forces are the forces that everything has. So hydrogen bonding is the bonding between hydrogen and more electronegative neighboring atoms such as oxygen and nitrogen. So, for example, this ammonia and water are attracted. The negative end of the ammonia is attracted to the positive end, the positive hydrogen, and this only happens with very electronegative elements. Fluorine, oxygen, and nitrogen bound to a hydrogen, and so they have to be small, very electronegative elements bound to hydrogen that give you hydrogen bonding. It's like a dipole interaction, but it's actually more advanced and a little bit stronger. So hydrogen bonding in DNA, thymine hydrogen bonds with adenine. This is why it's those two hydrogen bonding attractions are why T pairs with A in DNA. Same idea between C and G, cytosine hydrogen bonds to guanine, so we get those three interactions. So the reasons why T and A pair together with C and G pairing together is because of those hydrogen bonding interactions. When the enzyme unzips DNA, it's just breaking hydrogen bonds. That's why it's able to do it. So dipole-related forces, there's a lot of dipole-related forces. There's ion dipole, hydrogen bonding, dipole-dipole, ion-induced dipole, dipole-induced dipole. So stronger than dipole forces are ionic, metallic, and covalent bonding. Hydrogen bonding tends to be classified as a dipole force. Mostly we're going to focus on dipole-dipole, so polar molecules being attracted to other polar molecules. So London dispersion forces are the weakest. They are caused by the temporary separation of charge that leads to the London force attractions, are what attract one nonpolar molecule to its neighbor. London forces increase with the size of the molecule. So the bigger molecules have more electrons. Because they have more electrons, they can undergo this temporary separation of charge. And we're going to talk about what that is. They're sometimes called London forces, and dispersion interaction forces. So here's what it looks like. So let's look at the atom A and atom B. What happens is temporarily we get a slosh of electrons to one side. That slosh of electrons to one side of an atom or a molecule causes a temporary negative and positive end of that. Because that temporary negative and positive end occurs on an atom next to another atom, that other atom then has its own temporary polarization with its electron shifting to the positive side of the other molecule. And so what we end up with is this slosh of electrons that creates temporary positives and negatives, which induce other temporary positive and negatives in other molecules and atoms. And that causes everything, just by the nature of having a lot of electrons, to be attracted to one another because of the temporary positive and negative occurrences. This is what London dispersion forces are. To have London dispersion forces, you just have to have electrons, which means everything has London dispersion forces. So London dispersion forces in hydrocarbons, that's the only source of attraction, the only force of intermolecular attraction that hydrocarbons typically have. So as they get bigger, you get higher and higher boiling points because of the higher and higher London dispersion force interactions. So methane, you'll notice, is down around 100 Kelvin, well below the freezing point of water, well below what you would think of as cold, all the way up to C8H18, which has a boiling point in Kelvin of about 400. 273 is 0 Celsius, so you're looking at a relatively high thing, and this is octane, which is what we think of when we think of gasoline, because we have an octane rating. Well, gasoline's more complicated than that. It's not just octane, but this is in octane. So we can also look at some other things. So boiling point as a measure of intermolecular force attraction. So again, boiling points of H2O, HF, and NH3 and CH4. You'll notice going across, you'll notice that they start high and that it drops down with those first three and then follows the same trend as the other period. And what this is because hydrogen, oxygen, hydrogen, fluorine, nitrogen, hydrogen, hydrogen, nitrogen bonds all experience hydrogen bonding as well. So the rest of these in this series, the bottom ones just have London forces, London dispersion forces. On the top, the first three, they have hydrogen bonding, dipole-dipole interactions, and London dispersion forces. And then as we move to the right, you just get rid of those hydrogen bonding interactions, and you just follow a trend of dipole-dipole interactions and London forces as they go up. So they get bigger and they increase in boiling point, except for those that have that hydrogen bonding. And hydrogen bonding is just so much stronger of an intermolecular attraction.